Okay, so with this study, the shear, we look at a beam when it's subjected to bending, okay? Might be vertical bending or lateral bending, but let's see what happens when you have torsion. So shear due to torsion. So basically this is, so let's say you have a beam. I make a circular one, it's just easier. So now imagine this one is subjected to a torque. So there's two ways to draw the torque. Sometimes people draw an arrow, sorry, a line with two arrows, or you could just create a line over here. Let's say this would be the torque T. And let's say has a length L. Okay, and let's say the cross section to do the general case. Let's assume we deal with a tube. You have the inside radius and the outside radius. So in such a case, the shear is equal to T times R divided by J. Okay, so I use J, but sometimes in different textbooks they use I sub P, which is the polar moment of inertia. And this is basically the same thing. We have the I for the bending. You're gonna have a J for rotation. So the physical meaning of the J is how unlikely that structure is to torque, okay? To rotate about this axis. All right, and J here, the general expression for J for a tube is pi over 2 R outside to the fourth minus R inside to the fourth. Or if we rewrite the same expression in function of the diameter, pi over 32 outside diameter to the fourth minus inside diameter to the power 4. So this is the shear due to T. And next, the next thing they can ask you to find is the angle of twist. Which would be angle of twist phi equals to the torque times the length of the shaft times Gj. So again, these equations, I hope they kind of look familiar. You must have seen them in solid mechanics. Okay, so here just a comment as some people catch up on the writing. So if J is the resistance to resist the torque, okay, so the rotation around the torque. So if you look at this equation here, the bigger the J, the bigger is going to be the resistance, no? And the lower the J, the least. So which one will be able to resist more shear? Let's say a tube like this one with an outside radius and inside radius, or a solid shaft. Which one will be able to resist a higher stress? The tube or the shaft? By looking at the equation. No, because the J will be smaller for the tube, no? And since it's dividing, this should be bigger. And the reason of that is what? This is really equivalent, like if we do the I-beam, where was the I-beam thick? At the top and the bottom, no? Yeah. Where would be the shear important over here? Would be on the outside, no? Because this is the expression TR. So at R equals 0, what is the shear? 0, no? Should be maximum at the end. So supposedly a tube can withstand more shear than a solid shaft, let's say of the same diameter. But now, what is the problem? And that is a problem that many times some of the teams over here have, the Baja and the other one, is that they say, oh, they base everything on the shear, so it looks wonderful, we can save a lot of weight, but then what happens with the angle of twist? You want the angle of twist to be small, no? Otherwise, if you attach gears, which is what they do generally to the transmission shaft, this is going to skip, no? So this time you see, if J is small compared to the one of the shaft, then the angle of twist will be higher. So when you do the design, for example, of a transmission shaft, you need to take into consideration both. And if you do a transmission shaft, that's what is called a shaft, not tubes, no? Because you want to be able to transfer all the power that is given on the shaft to transfer it to the gears. If you have some angle of twist here, you're going to lose that energy into the deformation. All right. Okay, so let's do now a problem that combines a little bit of everything. All right, so in this example, what we have is some structure that is, so you have like a long tube over here. Then on this side of the tube, you weld another one over here. And then on this side of the tube here, around here, you put another one. Like this. And this one here will be fixed. So our coordinate system, the height will be Y. Now this will be the Z. And now this one here in this direction will be the X. And we have the following forces. So we have at point A over here, a force of 2,500 pounds. I'm not going to put the units. You have one here of 14,000 pounds. And then here you're going to have two. One up of 3,600 and one in that direction of 3,000. And let's see, we know the height over here. So let's see what will be the height. If I do it properly, it will be like this. I don't know which way to do it. So this point to this point. So let's say this one to this one here would be 6 feet. Oh, no. Oh, yeah, that's 6 feet. Now, the length of this one here is 8 feet in length. Between here A and B, so the total height over here is, I'll do it this way, 11 feet, and the length of this one is 5 feet. And I think that's all we need. And we know that the cross section of each one of the tubes so let's say we have, so would be so this is it would be XZ, and we need to find the stresses, let's say at point H. All right, so we'll see what that point is. So H, which basically I think is a point, I don't know, we'll see where it is. Okay, I don't know exactly where it is now. And we know that the outside diameter is 9 inches, and the inside diameter is 8 inches. So we need to determine the stresses at point H. So according to my figure, actually it looks like H is over here. Yeah, no, this one here is correct. Looks like it's correct. Okay. So we're gonna take as our origin the point over here. So this would be our origin over here, right in the middle. So let's see first, what would be the forces? So let's say forces and moments, okay? So over here, let's just the math giving you the answer. So let's say, we have point A, this will be point B over here on top, and this will be point C over here. So if we look at the figure, we have that F, the force at point A, will be what? Will be on the y direction, negative, so 0, minus 2,500, 0. We'll have that F of B will be what? Will be the same thing, will be 0, negative 14,000, and 0. And finally, F of C will be equal to what? So there is no X, 0. Now the Y will be equal to 3,600 and the Z to 3,000. Okay, so we know that what? We know that moment is force times arm, no? So let's find the arms. What would be the position of point A? Point A will be located at what? The X will be 0. The Y will be 11. And the Z will be 5. Okay, all this is in feet. We might have to move it to inches, but let's keep it in feet for now. Okay, similarly, we do point B. So will be point B located. So will be 0. $11 and 0. And R of C will be, so this time the 8 will be 8, the Y will be 6, and the Z will be 0. Okay, so we know the equation M. So this is by definition M equal R cross F. Okay, moment definition. Okay, so now we can just let the math giving us the answer. But let's not forget to follow the common sense over here. Okay, we have the figure. So we have the moment created by at point A. The moment at A will be equal to R sub A cross F sub A. So if we write that mathematically, what do we have? I, J, K. Then we need to put point A, which is 0, 11, 5. Okay, 0, 11, 5. And F sub A, which is 0, negative 2500, and 0. So if you do this calculation, what are you going to get? We get, so 0 here. This one would be 0 minus will be plus. So 5 times 2,500, that will be 12,500 on the X. And then since this is 0, this will give us 0 and 0. Okay. I hope you don't have any problem taking the cross product. Remember how to do the cross product? Okay. Now, let's do point B. But let's see what happens with point B, because let's see what the math is going to give us. But is point B going to create any moment about this point over here? It's just perpendicular, no? So it should not create a moment. So let's see what happened here. So M sub B, hopefully the math will work, R sub B times F sub B. So this will give us what? I, J, K. R sub B is equal to 0, 11, 0. And the F sub B was equal to 0 minus 14,000 and 0. So if you look at it, no matter what combination you do, we're going to get 0, no? We get 0, 0, 0. But we can put a comment saying, okay, makes sense. does not create any torque because F sub B acts actually on that tube. Okay, basically, if you look at this tube, this is a reference frame, this is an axial force, no? So this would create enormous stress. Okay, and let's do the same thing for M of C. Will be equal to R of C times F of C. Will give you I, J, K. So R sub C is 860. And F of C is 0, 3600, 3000. So if we do that, we're gonna get over here. So it will be, first one will be 18,000. That one is easy. Second one will be 24, so minus 24. And the last one will be 8 times 3600, so that's 34 plus 6 times 8, 40, so 28 and 100. And each one of these units, we need to be careful because this will be LB foot, LB foot, LB foot. Okay, so basically here, maybe I need to clarify something. That way we don't have to do a lot of problem, is that where are we trying to calculate the stresses at point H, which is located here at the root. Okay, so what did we just calculate it over here? The origin was at the root, no? Yeah, so we can say over here, so forces, so the forces and moments at point H are what? So it will be forces will be equal to F sub A plus F sub B plus F of C, which this will give you what? Let's see, F sub A is 0 minus 2500 plus 0 minus 14,000, 0 plus 0, 3600, 3000. So this will give us that the forces at point H, so let's say this is FH, one, will be equal to what? Will be equal to 0. So let's see, it will give what? This will be positive 1100. So this will be 12 minus 12, 1,900, and the last one will be 3,000. So basically, it should not be a height, but if we look at point H, I'm trying to look here at the figure. So we do this XZ. So let's say this is difficulty. This is what Z and X. So basically, what will you have? You will have no force on the X. You will have a 3,000 on the Z, and you will have a minus. So you have here a going down 12,900, and point H will be somewhere over here. Okay, so basically, if we look at this figure, 3,000 is creating really a bending, no, a moment, would be creating this deformation. This will be just in plane, just due to the forces, no? And these forces actually should be equal to what? We didn't do it, but it should be equal to what? If you calculate the reactions at this point, that should be equal to the reaction forces, no? Okay. All right, so we found the forces. Now let's find the moments. All right, so the moment would be equal to m sub A plus m sub B plus m sub C. We do the same thing. So in this case, we knew that m sub C was equal, no, m sub B is equal to 0. So I'm going to write it. So we have m sub A was equal to 12,500 plus m of C 18,000 minus 24,000 and 28,800. So basically, this is going to give us that the moment at point H is equal to what? So the first one will be 30,500. Second one would be minus 24,000. And the last one will be 28,800. And this is pound per foot. So as before, I'm going to do a little sketch. So let's say we have here X, we have here Z, here X. We know this is point H over here. But what I'm trying to plot here is because this is important, because that's the way for me to tell what would be the sign, okay, if there's any bending. So we know m sub X is positive. So that one should be going counterclockwise over here. So this is mx, if you want, equal to the 30,500. Now, my is negative. So that means that instead of going counterclockwise, it's going to go clockwise. So this will be my, which is actually just the torque. And this one is equal to 24,000. So as you can notice here, I dropped the sign because why? The sign is already on the direction, no? All right. And then the last one, Z, that one is positive. So that one should be going counterclockwise. So M of Z here will be equal to 28,800. Okay, so let me, since I have the other stuff at the other page, let's just do a quick summary here. Otherwise, I'm gonna have to be going back and forth between two pages, and this, I could just look at this page. So f of h we find out to be equal to 0, negative 12,900, 3,000, and mh 30,500 minus 24,000, 28,800. And don't forget, this is pounds per foot. Okay, so what we're going to do now is the problems, when they get complicated, the best thing is to break them down. So we're going to do one force at a time. So is the zero force going to create any shear? No, no stresses at all, no normal or tangential. So let's look at the force Fy. Let's say first Fy equal to negative 12,900 pound force. So we first look at that one. So if we do the figure for that one, like I did before, okay, if you can look at the other one, we have this one going in that direction. So what type of loading this is creating? It's creating axial stress, which will be equal to what? Force divided by the area. So what is the force? Is 12,900. I'm just putting the magnitudes for now. Then we can see about the signs. What would be the area? What would be this area? Pi r square, or pi over 4 d outside square minus d inside square. So if you want, let's go to the next page and put the values. Page 71, we're going to get sigma 1 equal to 12,900 divided by pi over 4. The outside was equal, I think, to 9 inches. Yes, so 9 square minus 8 square. And if you do the calculation, I think this should give you, let's see, have the result, 966 will be the units, pound force inch square, which is the same thing as PSI. Okay, but we're gonna add one thing to that result. Is this one in tension or compression? Compression, no? Yeah. I hope there's not a problem. So compression, you could put the negative value, but I don't like to put values. I'd rather just put here compression. And that's it. So we'll know it will be negative. Okay, so we did that force. Now we can do the force Fz. So for Fz equal to 3,000 pounds. So let me do another plot again. So we did the figure. The 3,000 was going to the left. But here, be careful. So this is producing a force of, so shear stress. But again, is that shear stress due to torsion, or is it due just to the force that is tangential to the area? This is not torsion, no? Just tangential. So what do we say about, so remember we're calculating everything at point H. So in this case, let's say our point H is here, okay? Doesn't matter, but let's say it doesn't matter where it is. Let's say it's here, okay? What would be the stress over there? Remember, what did we have for the I section? In order to have shear stress, you need to have one surface to rub against the other one. Is there any surface rubbing over here at point H? No, so we could say here that the shear stress at point H will be equal to what? 0. Is that understood? Okay, good. So we are done with the forces. Now we're going to do the same thing with the moments, okay, but only at point H. So the first moment we have is mx equal to 30,500 pounds per foot. It's important to put the foot because we're going to have to calculate everything in PSI, no? So that would be inches. Okay, so again, always redo a little figure. So we redo the little figure here. So we have been selecting the Y up, the Z in that direction, the X in that direction. Our point H is whatever, right here. I've been using the green for point H. Okay, so mx is positive, so it needs to go counterclockwise. We did it on the previous figure, so it's this way. So what type of loading is this going to induce over point H? Axial, shear due to torsion, or bending? It's going to create bending, no? Yeah, would be bending stress. So bending, the action would be here, bending. So if it's bending, what is the equation? Sorry, we have sigma 2 will be equal to what? Mx times y. The shear will be changing with respect to the cross section is on the x, z direction, no? So this will be mxz divided by I of x. Okay. Where we know that m of x is equal to 30,500. What would be z? Be careful, because 9 inches is what? This is the diameter. So it should be 4.5. Okay. Don't worry about that. So 4.5 inches. So now we need to be careful, because this is, you see, we need to be careful here, because this is what the units foot per pound, no? So we want to move that to inches. We need to multiply by 12, so that we're going to get pounds per inch. See, before I forget. And now the last one, the IXX for circular cross section. This you don't need to know it. If you have it on an exam, will be given to you. The equation is pi over 64 of the outside diameter to the power 4 minus inside diameter to the power 4. And I don't have the result, but I have the final result. So if you substitute, so that sigma sub 2 will be equal to whatever, 30,500 times 12 times 4.5 divided by pi over 64 of 9 to the 4 minus 8 to the 4. And if I did not do any mistake, this is equal to 13,612 psi. So now the question, with point HB in tension on compression due to mx, how would this be bending? Would be curving, I mean, it's hard, but it would be curving this way, no? Yes? So what would be point H due to mx? Tension or compression? Is compression. You see, this is like if it was, is like this, is bending like this, no? So this side is in tension, this side is in compression, no? And this is the side where H is. Can you see that? Okay. So H is in compression. All right, what else do we have for loads? Oh, we have, well, we need to look at My, but let's see what's going to happen with My. So My is equal to minus 24,000 pounds per foot. So again, I'm going to do a small figure like I did before. I mean, you see that figures are extremely important, no? There's no way to get results without figures. So Y, Z, X, this is our point H, and My is negative, meaning that it's going to go clockwise over here, but we see this time that really My, what it's doing is what? It's creating a torque. Yes? So now, what would be induced by the 24,000 would be shear due to torque or torsion. So shear due to torsion. And that's the equation we just did today. So we give you tau equals T times R divided by J. So if we follow the same thing as before, we can say where T will be equal to 24,000 times 12. Then R will be what? $4.5. So just one thing, if you needed to look at the distribution, because I didn't do it before on the equation, at the distribution of the shear, what will it be? We say at the beginning will be 0, no? Because R is 0. Yeah? Okay, so the distribution is that way. Okay, and now J will be the expression we had before, which is basically is pi over 32, if I remember right. D outside to the power 4 minus D inside to the power 4. So we substitute so that we're gonna get tau equal to 24,000 times 12 times 4.5 divided by pi over 32, 9 power 4 minus 8 power 4. And let's call this one the first shear, so tau sub 1. This is going to give us 5,355 PSI. Okay. Or will be mz. So it will be what is created by the moment mz, which is equal to 28,800 pounds per foot. So following the same procedure as before, I'm going to do a little figure here. Then I do the X. So Y, C, X. I put here the point H. Because everything we're doing is at point H, and this time MZ is positive, so it's coming out. So MZ equal to 28,000 will be good. So what type of stress is going to produce that moment? Is it going to be torsion or bending? Bending. So it will be, as we said before, it's going to induce bending stress. Okay, so what would be the equation? We have sigma 1, sigma 2, so it should be sigma 3. So the equation will be sigma equal to, so sigma 3, let's put it right away. We deal with the moment Z. So that means that we need to have here X, and this will be I of Z. So let me ask you a quick question. Can you tell me right away what is the stress at point H? What would be the neutral axis? Would be where? Z, okay. So what would be the distance between, what distance will be H from in the X direction? Zero. So that would mean that the stress is zero, no? So this is X equals 0 because it's on the neutral axis. And what do you know? What is the definition of the neutral axis? And the neutral axis is where the stress is 0. Okay? So this means sigma 3 equal to 0. 0 psi. So basically, if you remember, even if this is circular cross section, if this is the neutral axis, how is the distribution of the stresses? Is 0 at the neutral axis, no? Yeah. And here what happens is that point H, I mean, I don't know on which side it will be, but it will be right about the neutral axis. Yes? Okay. So I think we got everything. Almost done with this problem. 73. Okay, so let's say finally, the stresses or the stress at point H is what? So we're gonna have sigma H equal to sigma sub 1 plus sigma sub 2 plus sigma sub 3, which will be what? Sigma sub 1, we had 966 plus 13. Here, be careful because both these ones are both in compression, no? So we can add them together, plus 0. So this is going to give us that sigma H is equal to 14,578 psi. In compression, and the shear is equal to what? What do we have? Tau 1 plus tau sub 2. So tau 1 was 5,355 plus tau 2 was 0, no? I don't see it. I don't see what page it is. Oh, we didn't call it. So we call it, this one is tau H, no? The one we call tau H, which is 0. So basically this will give you that tau sub H equal to 5,355 psi. Okay, and something I forgot probably to mention is that when we talk about shear, there is not really tension or compression. There is not really positive or negative, no? I mean, there is positive or negative, but this will tell you the direction of the shear. But remember what did we say last time is that if you look at a cross section, the shear will be what? All the shears should be equal to 0, no? So actually a positive shear means that this is a distribution of a positive shear, and that a negative shear, but I mean, to tell the truth, I never pay attention to this. And negative shear will be the opposite. Will mean this. All right, so let's go back to our initial problem, to the problem statement. 1, 2, 3, 4, 5, 6. Okay, so now imagine that I ask you to find the deflection at point A. Would that be fun? Not fun at all, okay? It will take you forever. What would be the way to do that? We're not gonna do it, but why I have been giving you complicated loads for a beam? Let's say if you wanted to replace this just by one beam, what could you do? You could replace this by one beam, but then at this point you will have to add an axial force plus the moment created by this, no? And you could eliminate this member over here. At the top, you could do the same thing. You could put the force plus the moment created with the moment over here, no? Yeah? And now you could just study the stresses along this one due to that load distribution. It should give you the same result. Okay? After doing that, you could calculate what would be the deformation at this point and this point. And then you can assume, so you can find the deformation. I don't know if you follow. Then you can assume this one to just be fixed, no? So you can find what will be the deformation in this direction. You can add the deformation just of this piece here by assuming this is fixed, plus the one you calculated before, if we give you some type of approximation. But it would just be an approximation because it would not take into consideration the shear. All right, I mean, anyway. So what would be the easy solution? By now, you should know the answer. Final elements. So when you do a finite element, you don't need to validate everything you calculate. Let's say if you validate the stresses, you can assume that the deformation will be correct. Okay? Well, you find the correct deformation, you can assume that the stresses will be correct. So here, let's try to do a model quick. Help me a little bit. So this is the new model. So generally, I like to do it from here. Material is not important, the material, because we're not calculating deformation. Anyway, this is in English units. So let's take steel. You could take anything you wanted. It's not going to change anything. Properties, we're going to take, again, our beam. All right. Shape, we are dealing with a tube. What is the radius? I think the outside was 9. So what would be the thickness? If it's 1, but it would be 1 all across. So the thickness would be 0.5. Does that make sense? So 0.5, and here I just like to do this because I like to put the y up to know where the y is going up. So I know the y is going up. And here you see all these values that we calculated. The IP, the J we calculated here is called I sub P. This would be our J, no? Okay, the I sub P over here. That's why I also say that sometimes they call it I sub P. And this will be the IX, this will be the, oh, here it is. The IZ and IX, no? Might be changed over here. You can get the values from here. Okay, so, all right. And okay. So now let's see, we have the points over here. So let's create some points. So let's say, okay, model, let's do geometry points. Let's create points. So the first one would be a 0, 0, 0, which is at the bottom, which is this one over here. Now I'm going to create this one up, which is 11. So let's create one in the middle. So it will be 6, 11. Okay. Oops. We're going to create one at 6. Another one at 11. Okay, let's see if we are doing this right. So we should have 3 points. So this one, this one, this one. Now let's generate, let's see, this point over here. So this point should be at what? At 6? No. Yeah, should be equal at 6 and 8, no? So 6 up and 8 on the X. Oops, I did a mistake here. What mistake did I do? This is in feet. We want everything in inches. So you see, so delete geometry all. There we go. So we start from 0. All right, so help me a little bit here. 0.00. Then we're gonna get the point 11 times 12. And the point 6 times 12. Plus the point this one, plus the one that's moving on the X over here will be 8 times 12. So, and that will be X, no? I mean, help me a little bit here. 8 times 12. Is that correct? Let me double check. Yeah, 8 times 12. Okay, now at 11 times 12, we're gonna have the, what is it? 5 times 12. The, on the X or the Z was? Z, okay. 5 times 12. Okay, so let's see if that makes sense. Control A. I don't know. I'm getting a bit lost here.
Yeah, that makes sense.
All right, so let's see. Yeah, once we do the lines, we'll have a better idea. So methods points. So let's say we go from here to here, from here to here. That would be the, this would be now the top one. Oops. What happened here? Geometry, curve line, project points. From here to here. All right. I don't know. Curve line. Oh, points. Maybe it's that. Let's try this one. Maybe I'm clicking on the wrong here. Point 3 to point this one. Okay, I don't know what happened before. This one to this one. Oh, because I was clicking enter. So okay, I see now. So does that make sense? Yeah, that kind of look kind of correct, no? So now I'm going to do mesh control, size along curve. So this was, oh, how many we want over here? Really should not matter. Let's put here 6 and 6, doesn't matter. I think it should work. This one we're gonna put also 6. Whatever, I'm doing whatever here. And 6. Cancel. Now I'm gonna mesh. So now be careful with the mesh. Mesh, no, geometry, mesh control. Geometry curve. So we need to, okay, so if we mesh this one and this one, remember what would be the direction of the Y is going up, no? So we don't want that. You want the Y to be either on the X or Y direction. So basically to be lateral, no? Let's see if I'm doing it right. So I do this. So basically what I'm saying is that now, let's see, this is correct. You should have it this way, no? Okay. Now we do the same thing with the other ones. Geometry, curve, this one and this one. Now, yeah, the Y can be up. It shouldn't matter. Okay. Okay. So it's not the X, the Y can be up. So preview, yeah, and okay. So now you see this will be the way it looks like. Does that look correct here? What? Right, file, save as, desktop model 5. I don't know what all these models are. If you want one day, I'll give you all those models. I don't know what they are, but all right. So let me eliminate now this and go to F. Be careful here with the loads. Okay, no, it should not be that difficult. So model, constraint, nodal, so it will be whatever, fix. You don't have to put anything, which is what I do most of the time. This one will be fixed. Okay, now forces, what did we have? Model, load, nodal. Let's say forces. If you had moments, you could support the moments. So let's see, the one at the top is equal to negative 14,000. Now this one, negative 2,500. And this one, we had 2, positive 3,600. And on the Z, 3,000. Does that look correct? All right. Now you need to do one thing to check tools. Check. Is it a check somewhere? Check. Coincident nodes. Select all, and I think here you should have one here and one at the top. Okay. Preview. You see one here, one here. Basically, is where there's a connection between the different elements. Okay. Done. Okay, so that's it. If I always do this, doesn't do anything, but we should run it. Oh, create any new set, new, okay, analyze. Okay, so now this is the problem all the time that I have with this type of element is that, let's see, this is not what I want to do. F8, so let's see XY top. You see, it's always this one. You see the coordinate system is not exactly the same as the one we have, no? So that's always create a problem. So if we want to look at the stress, what I'm trying to say is that at first sight, let's see what I'm trying to say here is that I don't know if we need to select point 1, 2, 3, or 4, no? Just because this is oriented differently on the coordinate system. So we can give, I think what happened here is that our X, these are rotated. You see Z, this is our Z and this is our X. So my guess will be that point H is 0.3, but it's a guess, okay? An educated guess. So, okay, so let's do F5. We want to find the stresses. So combined stresses, what do we say, 0.3? Hopefully that would be it. Okay, F5, I need to show something. So that doesn't look like it's 0.4, 0.3, as you can see. So let's try another one. You see, my guess could be completely wrong. Let's try 0.4. This one makes more sense. Oh, well, let me eliminate this. Okay, guys, I just went back into here, the properties. We had a mistake here. We put 9 inches for the radius, but actually it's 4.5. We use the diameter. Okay, okay. So I'm going to delete these results over here. File, rebuild, yes, and we're going to rerun it. Okay, I think it's done. So maybe let's put this again, see if it works. Let's try to use this one as we did the other day. Advanced post-processing, beam cross-section. We're going to select this element here. But why is not showing that element here? I thought we were able to see the distribution the other day. We can't see it here, but maybe we need to isolate that one. Okay, so let's see. Axial stress. Let's see the combined stress. But at which point? We don't know. But let's see, this is still the same values as before. So all results. All right, let's try again the one we did before. This is 0.2. So let's try, let's try all the points. 0.1. Okay, these values are higher. So I don't think it's that one, but this one is one in compression. So that would be, what was our result? How much? 14. So this is giving 1388. So let's see what would be 0.2. So last time I think it was 0.3, the one I thought it was. So let's check 0.3. That one is a bit lower, so that's not a good guess. Actually, it should be up and down. Okay, so what is the other option that we have left? 0.4, which is the one you say, guys. So it looks like the one that was the closer is 0.2, no? 0.1 was the highest. So let's try 0.1. 12. Now we got 11 and 0.2. So we had a 13. No. Oh, he's the 14 here. So this is the 14,578. So basically, here, guys, because we lack of time, so I'm running a little bit, but basically what I'm trying to find over here is that which one of these points we're trying to calculate, no? So my guess will be either 0.4 or 0.2. Which one did we select at the end? 0.2. So you see this is reverse. So is this one, our 0.8 should be over here. But it's not that obvious, okay? I agree with you, because this coordinate system is like reverse. We use Z and X. Here they're using Y and Z, no? So it can be confusing. But basically, let's just keep this one 0.3. And let's see what will give us then the shear. So let's see if we can do the shear with the view. Advanced post-processing, this one. We select this element here. This one here. And last time we found that one by looking at the combined shear. Yes. We are looking at this element here, no? Yeah. So F5. What am I doing? View, advanced post-processing, beam cross-section. We're going to select this element here, combined shear, and it should give you the value. What is the value that we had? 53.55. So I don't know if that's the scale for this one, but basically this will give you 57.84, looks like, okay? I don't know exactly what will be the value. I don't know why it should not be more accurate. So let's see what would that give you. 57.84, the Z, 53.72. This would be the stress. Yeah, no, this is the von Mises, so it's not good. So I think last time we found the closest one being the combined shear stress. So here we had, again, 5,355. Here it looks like we're looking at, or maybe it's not the same location, you know?
I think it's correct there. It's in like the dark orange region.
Okay, yeah, I don't know where point, because maybe it's right here, so it should be somewhere in between. You see what I mean? So it will be like bottom left, so should be like, looks like it's this one here to me, but I don't know. Anyway, we have to spend more time to really see at what is the direction of the current system and know if we're looking at this point here or this point here or this point here, no? Okay. But anyway, now that you have this, it will be very easy for you to just say, if you want to look at the deformation, you don't have to do the calculation. Let's say you look at the translation for these ones, and how would this deform? Because this stuff is not deforming. So this will be deforming 1.592, no? I just put the contour here. Should not give any contour, but oh yeah, it gives contour. So basically this will be deforming. You can animate if you want, and you could see what would be the stresses throughout the deformation. All right, so we stop over here.